Hi guys. In this next few videos we'll be looking at circular motion and as it pertains to the Year 12 study design. So all we've got to remember is that circular motion is any motion that follows a circular path. Okay, it could be a horizontal circle, it could be a vertical circle, so long as the object is moving in some kind of circular path, or at least part of a circular path, then we can consider that object to be in circular motion. Now, in Year 12, we are going to be concerned with, first of all, uniform circular motion. So this is circular motion that the speed of which does not vary. Okay, the speed is constant throughout the motion. And we normally look at this kind of motion in a horizontal plane. So the circle, or rather the circular path, is horizontal. Okay, so think about like a ball tethered to a string that's attached to a pole, and you're hitting this ball around the pole. The ball will move in a horizontal circular path. Okay, or consider someone doing a hammer toss at the Olympics. They sort of move the hammer in a circular path above their head, ready to throw it away. Okay, that's a horizontal circular path. Okay, and we're considering uniform circular motion in those paths. Okay, so constant speed. The other path, or the other kind of circular motion we'll be looking at, is non-uniform. So that means your speed is allowed to vary, and pretty much all of the time that we look at non-uniform, it's going to be in the context of a vertical plane. Okay, the circle is a vertical circle, so think of, like a roller coaster doing a loop-the-loop. All right, it follows a roughly circular path when it does that, and you should be able to imagine the speed varying throughout that motion. Okay, in Year 12, we're only going to be looking at the top and bottom of vertical circular paths. Okay, in terms of the forces that are acting at those points. So, to start talking about circles, we need to define some things. The first thing we're defining is the period. Okay, so the period of uniform circular motion is the time taken to complete one full revolution. Okay, we measured this in seconds. So you can imagine something moving in a circular path. So let's imagine like a planet going around the sun. Okay, that's roughly circular. And the time that it takes to go around once, so there might be the sun in the middle, this might be Earth. Okay, the time it takes for the Earth to orbit the sun once, that's called a period. Okay, and we measure that in seconds. For us on Earth, that takes about 365 days. But if we're using it in a calculation, then we should convert that to seconds. Okay, so it's just the amount of time that it takes for an object to complete one full cycle of a circular path. Related to this is the frequency, which we give the symbol F. And this is equal to the number of full revolutions completed in 1 second. Okay, so let's say I'm swinging a hammer above my head, like in the hammer toss, and I make that hammer move once around the circle every 1 second. Okay, that means it has a frequency of 1, and we measure the frequency in a unit called hertz, which is just basically number per second. Okay, so if I complete 1 revolution in 1 second, it's got a frequency of 1. If I complete 2 revolutions in 1 second, so the object's moving slightly faster, then it has a frequency of 2 hertz. Okay, and the period and the frequency are related using these formulas here. Okay, so if it takes, let's say, half a second for me to complete 1 revolution, so that would be the period. The period is half a second. Then in 1 second, you should imagine that I can complete 2 revolutions. Okay, and that means the frequency would be 2. Okay, and we can relate those two things together by saying that the frequency is equal to 1 over the period. And if we do that, we get 1 over 0.5, which is 2. And it works the other way as well. Okay, if I know the frequency and I want to work out the period, I do 1 divided by the frequency. If we're using the example just given here, 1 divided by 2 is 0.5 seconds. Okay, so that's period, the time it takes for an object to complete one revolution, and the frequency is the number of revolutions completed in 1 second. Okay? All right, let's talk about the speed of an object in circular motion. So, the average speed. Now remember, we defined average speed when we did our motion review ages ago. The average speed of an object is defined as the total distance that object has traveled divided by the time taken to travel that distance. Okay? Now, if you imagine an object in uniform circular motion, so we're assuming that the speed is constant in this motion, then the average speed of that object should be equal to its instantaneous speed. Okay? If your speed is not changing throughout a particular instance of motion, then your average speed should be equal to the instantaneous. Okay? But let's talk about the object in circular motion. Okay, so the object's going around in a circle, like that. Okay, and it has completed one period. Okay, now, if that is the radius of this particular circle, how far has that object traveled in one period? Well, that would just be the circumference of that circular path, right? Okay, so the distance that this object has traveled is just the circumference, 2 pi r of that circle, if we know the radius. And the time taken to complete that journey is just the period, okay? Because the period is the time taken to complete one full revolution. So we know the total distance traveled. We know the time taken to travel that distance. Therefore, the average speed, and thus the instantaneous speed, should be equal to distance over time, which is 2 pi r over t. And then we have this nice little formula here, allowing us to calculate the velocity or the speed at any point during that circular motion. All right, now we're going to talk about the acceleration of the object. So you've got to remember, okay, Newton's first law says an object will remain in a constant state of motion unless acted upon by a non-zero net force. Okay, so what that means is that the object will either remain stationary or have a constant velocity unless acted upon by a non-zero net force. Now, an object in circular motion, you got to remember velocity is a vector. Okay, it's the speed and the direction in which that object is moving. So if you think of this object, say here in this picture, okay, at any given point, the velocity is always going to be pointing at some not random, I shouldn't say random, it's going to be pointing at some other direction than any other point on that particular circular motion. Okay, so up here, the velocity is pointing, at that instant, the velocity is pointing straight towards the left. And then if we go a quarter of the way around, the velocity is now pointing down. If we go another quarter, the velocity is pointing to the right. Another quarter, the velocity is pointing up. Okay, so at all points on this motion, the velocity is changing. Now, if the velocity is changing, then according to Newton's first law, there must be some kind of non-zero net force acting on the object. And thus, if there's a non-zero net force acting on the object, then according to Newton's second law, there must be an acceleration of this object, okay? And in terms of an object in circular motion, the acceleration of that object is always going to be pointing towards the center. Okay, and there's a derivation that we can go through in your book. It's not really that important, but the acceleration of this object is always going to be pointing towards the center of the circular path. Okay, so just keep that in mind. Now, if we use our, we've got this formula for acceleration. Again, we're not going to derive this. There is a derivation in your book. But it's not that important to know how we derive that. Go and look at it if you're interested. We're just going to save a bit of time here and not worry about it. But we can derive a formula for the acceleration of an object if we know its velocity, its average speed in this circle, as well as the radius. Okay, and this is very, very particular. This is only relevant for objects in circular motion. Okay, so only for circular motion. Okay, now if I go back a couple of slides and we use this formula here for the velocity and I substitute that formula into my formula for acceleration, okay, we get this nice little equation here relating the radius of the circular path and the period to the acceleration. Okay, so this is a formula that you should probably write down. This is going to come up again when we talk about gravitational fields and objects in orbit around other objects and things like that. Okay, so it's a really important formula. We're going to use it quite often. Maybe not so much in this section, but it will pop up again in other sections. Okay, so write that down. Also write this one down, and you might as well write that one down too, somewhere. Okay, so what did we just say? There's an acceleration pointing towards the center of the circle. Therefore, because net force is equal to mass times acceleration, because those two things are vectors, then it stands to reason that the net force must point in the same direction as the acceleration. Okay, and in terms of a circular motion, that means the net force points towards the center of the circular path. So there must be some kind of force acting on your object that's causing it to continuously change its velocity. That force is always pointing towards the center of the circle, okay? And here are just some examples of circular motion for different kinds of objects. So in the first one, that's what we were talking about with the hammer toss, okay? The force that is being provided to this object in circular motion, this hammer, is the tension that this person is using to swing around the ball, okay? Now we have a name for this force that's pointing towards the center. It's called centripetal force. Centripetal is just a fancy word for saying center seeking. Okay, so the force points towards the center of the circle. It's center seeking. Okay, centripetal. So that's the example with the hammer toss. Here we've got a satellite in orbit around the Earth. Okay, and you can see that it's going to be the gravitational force that's providing the centripetal force for the circular motion. Okay, so there is this force of gravity that the Earth is exerting on this satellite, and it will always point towards the center of that orbit, the center of that circular path. In C, we've got a car going around a corner quite fast, and in order for the car to not sort of slide off the road that way, okay, you've got to picture it, there's got to be some kind of force preventing that car from just going off that way, okay, and that's the friction between the tires and the road. Okay, so the road is exerting a force on the tires of the car that are pointing towards the center of the circular path. And you can imagine that the radius of this circular bit of road might be over here, and so the force points in that direction. Okay, so the friction between the road and the tires is what keeps your car going around a roundabout rather than just sort of flying off the road into the ditch. All right, now in this last picture here, we've got picture D. This is some kind of carnival ride where there's a person sort of in a cage. I don't know if you've ever seen it, but there's this particular ride where you're in a cage and the ride sort of goes in a circle around and around really quickly, and you sort of feel pushed towards the back of that cage. So this person feels like they're being sort of squashed against the back wall here. All right. And what's going on there is because this person is confined in this cage and the cage is going in circular motion, then there must be some kind of force acting on this person to keep them in circular motion. And that force is the normal force, the contact force between the wall and the person. So the wall is exerting a force on the person towards the center of the circle over here somewhere, keeping them in circular motion. And the reason that this person would feel sort of thrown out isn't because there's a force pulling them backwards to the back wall. It's because that person wants to continue going in a straight line, all right? But the wall is forcing them to sort of curve their motion around like that, okay? And this is Newton's first law again. And so that person feels like they want to go that way, but they can't. So they feel like there's some kind of force pushing them backwards, okay? That's sometimes called the centrifugal force. Centrifugal force. Centrifugal. Okay, it's technically not a real force that we use to analyze problems, but we can set up coordinate systems and things like that. So it is a real force, but we're not going to get into that now. Anyway, these are just some examples of objects in circular motion and the forces that are providing that circular motion. Right, just quickly, we can describe the net force acting on that object. If you just remember net force equals mass times acceleration, we have an expression for the acceleration of an object, okay, in circular motion. Again, we're not going to derive it, we're just going to give it here. If we substitute this into F equals ma, then we get this nice little formula here. And you'll see when we do circular force questions, we'll do what we've done before. We'll say F net equals, and then we'll sum the forces in a particular direction, and that will give you whatever, and then we'll make that net force equal to mv squared on r. And you might be given the velocity and the radius and something else, and you might have to work out, say, friction or a component of the normal force or something like that. Okay, so that's what you'll see me be writing out. That's a really important equation to remember. Okay, if we go and use the other version of our acceleration that we did here, where I substituted the expression for velocity into the acceleration, then I'm just putting that thing here into net force, and we get this expression here. Okay, this is a bit less common. Don't really see that being used too much, but it's still an equation that you should write down. Okay. Right, we're going to stop there, and next we'll look at some problems. See you then.